All right, welcome to Chapter 6, Circular Motion, Orbits, and Gravity. So this one we're going to introduce a lot of new equations, but the good news is that all of the equations are kind of similar, and they all make some logical sense, and then it's just a matter of using them in different ways. Okay, so let's start with a reminder of objects moving in a circle. So as objects move in a circle, they have velocity that is tangential to the edge of that circle. We call that tangential velocity. It's the instantaneous velocity at a tangent. Then the acceleration is always towards the center of the circle. So the acceleration always goes in. And remember, that's because you take the previous tangential velocity. So like that was the previous tangential velocity. And if I superimpose that to there, up there, and then do a subtraction. So then this one minus this one. So that would be taking it back down there. What I end up with is the change of velocity. So a subtraction just meant I flipped it backwards. The change of velocity is my acceleration, and acceleration always ends up towards the center of a circle. We call that centripetal acceleration. And we can solve for it and find that the centripetal acceleration is velocity squared over r. You might remember this one from a previous chapter, but it is important. Specifically, centripetal acceleration is always towards the center of the circle. And so since it's important, it is on your physics AP cheat sheet, and I've highlighted it in green and labeled it centripetal acceleration, and then I drew a little circle motion next to it just so I remembered what it was. So that's a big key one there. And we're also going to add some additional terms on here. Okay. So I can take that centripetal acceleration, I can play around with it a little bit. So I know that frequency, how often something happens, is 1 divided by the period. So the frequency is like the number of times per second. So that would be 1 divided by the period, which is the seconds that it takes for the circle to happen, right? If it takes 2 seconds per circle, then the frequency would be 1/2, 1 circle every 2 seconds. All right. I also know that velocity is equal to distance over time. But if I'm going in a circle, then I have a special distance. The distance that I'm going to use is the circumference of the circle, and that's 2 pi r. And then I could divide that by the period, which is the amount of time that it takes to go around the circle. So I've got distance over time, or 2 pi r over t. And that stands for the velocity. Now I can substitute that in for the velocity part, or I could change it and say velocity is 2 pi r times the frequency, because 1 over t is equal to the frequency. And that gets me to here. And then I can take that velocity and substitute it in for the velocity on centripetal acceleration. So now I've got 2 pi r times the frequency squared over r. And then if I simplify that, I can take one of the r's away. So take away the square on one of those r's and cancel the r on the bottom, and gives me an r on the outside. 2 pi frequency squared equals the acceleration, or 2 pi over the period squared times the radius equals the centripetal acceleration. So all of these are different versions depending on what's given to me. If I am given the frequency and the radius, and I need the centripetal acceleration, then I've got an equation for that. If I'm given the radius and the period, and I need the centripetal acceleration, I've got an equation for that. All of these can be derived from each other, so you can play around with them a little bit. I would say big ones to focus on would be this guy, right? That is equal to v. So the velocity is 2 pi r over t. And then you've got, obviously, the centripetal acceleration, and then variations around that. All right, so let's find the period of a carnival ride. In the quasar carnival ride, the passengers travel in a horizontal 5-meter radius circle. For safe operation, the maximum sustained acceleration that riders may experience is 20 meters per second squared, approximately twice the freefall acceleration. What's the period of the ride when it's being operated at the maximum acceleration? So I need what is the period, so that's a need of t, and I'm given an acceleration, which was 20 meters per second squared, and I'm given a 5-meter radius. Okay, so acceleration, radius, and period. Oh, look at that. I've got that equation right above it, right there. So I'm going to do acceleration is equal to 2 pi over t, squared times r. Now I'm just going to plug straight in. I could manipulate it like this and do square roots and what have you, but instead I'm just going to plug in my values. So that is 20 meters per second squared equals 2 pi over the period, that's what I'm solving for, square that, times the radius of 5 meters. So I need to isolate that, divide both sides by 5 meters. That'll get rid of that and leave me with 20 divided by 5, not the same as 20. That leaves me with 4 1 over second squared equals 2 pi over t squared. So now I need to do a square root on each of them. Conveniently, the square root of 4 is an easy one, giving me 2 1 over seconds equals 2 pi over t, multiply by t, divide by 2, and I get an answer of, so this is times t, divided by 2, 1 over seconds, divided by 2, 1 over seconds. The 2's will cancel each other. The t's have canceled, and I'm left with pi seconds. So t equals pi seconds, or 3.14 seconds. Cool. So does that make sense that they could spin around at 3 seconds per go? Yeah, that seems to make sense. How fast are the riders moving when the ride is operated at this period? Okay, so now I need the velocity, and I know that velocity is equal to distance over time, which is equal to 2 pi r over the period. Luckily, I've just solved for the period. So now it's 2 pi times 5.0 meters over 3.14. Let's see, the pi's will cancel, right? And my velocity is 10 meters per second, because that's seconds is the unit there. Okay, that seems reasonable. 10 meters per second, 22 miles an hour. That seems like a good, fun spinning ride speed. Great. All right, let's do a stop and think. Rank in order from largest to smallest the period of the motion of particles A to D. Okay, so period is how long it'll take to go around. And I have period would be, let's see, I need to solve here for period with velocity and radius. So I've got this equation up top, this guy right here, because it's velocity and radius. So if I multiplied t over and then divided by v, radius and so radius would make it go more time, more velocity would make it go less time, and they are kind of directly related. So let's check that out. All right, so bigger radius, more time. So 2r is going to take more time. And then less radius would be less time. Faster, let's see, period is the amount of time. So the faster it goes, the less time it is. So that would be less less. And then the slower it goes, it would go faster, more and more. Okay, so the largest period would be my two greens, right? More, more. So I'm going to say C is the largest, right? C is going to be, let's do it in black. C is going to be my greatest period. And that's going to be bigger than, well, both of these ones, VR and 2V2R, since my equation would put effectively V over R, sorry, R over V, since my equation puts R directly over V, R over V, or 2R over 2V ends up the same. So I would end up with D and A the same. So A equals D, and that would go in the middle. And then my smallest one would be going fast in a small circle. Fast in a small circle is going to happen real quick because it's not going as far and it's going it faster. So then B would be my smallest time period. Nice. I think I feel pretty good on that. Lovely. So let's kind of keep moving. Net force. Okay, so we talked about acceleration, like centripetal acceleration, but net force is equal to mass times acceleration. So if I plug in my centripetal acceleration value here, v squared over r, and then multiply by mass, I can get mass times velocity squared over r, mv squared over r. And they go towards the center of the circle. So the net force is towards the center of a circle. So here's a little diagram of it. It looks really similar to our previous diagram. Acceleration's towards the center, and so the net force is also towards the center. It's just multiplied by the mass. And the net force could be from a variety of different factors. It could be from the normal force, if you're going around down a dip. It could be from the kinetic friction force, car going around a corner, and it's the tires not skidding that's keeping it in the circle. It could be from the weight, just any force that could be pushing it. All right, so let's do a little sample. Finding the maximum speed to turn a corner. So what is the maximum speed with which a 1,500 kilogram car can make a turn around a curve of a radius of 20 meters on a level, unbanked road without sliding? The turn radius is about what you might expect at a major intersection in a city. Okay, so I'm turning a corner, doing a right hand or left hand turn. It doesn't tell me whether it's the radius of a right hand or a left hand turn, but I've got a 1,500 kilogram car. I have my radius, and then I noted that I assume that the car has tires on it, and that the road is made of concrete or asphalt. So if that's true, then I can say that the coefficient of friction for rubber on concrete is 1.0. And that's the static coefficient of friction, because I don't want this thing to slide out, right? If it's already sliding, then I have a problem. So I need to maintain the static coefficient of friction so that the tires don't slide sideways out. I'm not talking about them rolling. I'm talking about them skidding out. All right. I also know that the force of static friction is equal to mu sub n, the coefficient of friction times the normal force, and that the static friction is equal to the net force, which is mass times velocity squared times the radius. So let's set those equal to each other. So mu sub s times the normal force equals the mass times the velocity squared over r. Now I also know that the normal force, since the car is on a horizontal surface, there's no bank, there's no slope, the normal force is equal to the weight. Normal force up, weight down. And the weight is equal to mass times gravity. So I do mu sub s mass times acceleration due to gravity equals mass times velocity squared over r. All right, now I can go back through and I've got mass of the car on both sides, so those will cancel out. I've got that, I've got that. I need the velocity, how fast it can go, and I have a radius, which is 20 meters. Okay, let's plug it in. So 1.0 times 9.8 meters per second squared equals the velocity squared, that's what I'm solving for, over the radius, 20 meters, multiply both sides by 20 meters times 20 meters. The 1 is going to be pretty irrelevant, anything times 1. 20 times 9.8 will give me 196 meters squared per second squared equals v squared. Take the square root of that. And I feel like I should know the answer. It's like 13, 14. I think it's 14. So I'm going to say velocity equals 14 meters per second. 196 looks familiar, but I'm just going to double check it because I don't remember my square roots that well. It is. Yep, good. So my maximum speed would be about 14 meters per second. That'd be somewhere between 30 and 35 miles an hour. That seems reasonable. Yeah, I don't want to go tearing around the corner much faster than 30 or 35, especially if it's a tight right-hand turn. Yeah. All right, let's do another stop and think. A block on a string spins in a horizontal circle on a frictionless table. Rank in order from largest to smallest the tensions acting on the blocks A to E. Okay. Oh, these are good. Okay, so I've got frequencies and radii. So the radius in this case got 2 times bigger there and 2 times bigger there. The frequency, this is the number of spins per minute, revolutions per minute, is going 50, 50, 100, 100, 100, or 200, 200. Okay, so I need to find an equation that relates frequency, radius, and force. Now the mass of the block is the same every time. So I think I would use tension equals force, which is the mass times the centripetal acceleration, v squared over r. But then the v is going to be based off of the frequency. And so, let's see, I'm going to go back up to the top and check in on my v to frequency thing. Here is one for frequency. So I'm going to use this equation since it has frequency in there. So that's actually 2 pi frequency squared times r is my acceleration. All right. I'm going to go back and double check that one. So I'm going to have to try a different equation. M times, where am I? There we go. So that was mass times 2 pi frequency squared times r, because that was my centripetal acceleration. Okay, so frequency is going to be squared. Let's see, stuff that I can ignore. The mass I can ignore because it stays the same the whole time. 2 pi is a constant, so I can ignore that. So the tension is proportional to frequency squared times the radius. Okay, so I want bigger frequencies and bigger radii, but the frequency one is going to be the biggest difference to maximize the tension. Okay, frequency squared over radius. Yeah, that makes sense. All right, so the frequency squared, this guy is the biggest radius and the biggest frequency. So largest is going to be tension of E. That's the biggest. Okay. Now, the next one is I have one at 40 with 100 RPMs and one at 20 with 100 RPMs because I want the radius to be bigger and the frequency to be bigger. So this one has a bigger radius and the biggest frequency. Okay, so I think that's the tension of D would come next. Force equals mass times acceleration. I just want to double check this. It feels too easy. Force equals mass times acceleration. Acceleration is 2 pi frequency. Yeah. All right. Okay. Now, frequency squared, 100 squared times 20. Okay, that would be the tension of C. Then 50 squared times 20 is going to be better than 50 squared times 10. So tension of B. And then lastly, I have the tension of A is going to be the smallest. It is going the slowest, and it's going on the smallest track. So doing the least turns on the smallest track, that makes sense. Okay. Doing the most turns on the biggest track, that would lead to more tension. Cool. So that seems to make sense. All right. Centrifugal force. So centripetal force is that force towards the center of the circle, right? The net force to the center of the circle is centripetal force or centripetal acceleration. Centrifugal force is the one that we talk about all the time, but it's not really real. So centrifugal force is not real. It's the feeling of wanting to keep going in a straight line while you are turning. So while I'm making a turn, what's happening here is if I zoom in, I'm in a car. The normal force is going to push me in towards the center. My velocity wants to keep going. So what happens is if I'm here, my velocity wants me to keep going in a straight line out to here. But the car turns. So the car right here is going to end up on the road over here. So I want to be out here, but I'm actually over here. When I'm here, I have this feeling like I want to go out there, but there's no actual force there. The force is the real thing, and the real thing is the friction of the tires that is towards the center, right? We've established that a centripetal acceleration is the real force. So centrifugal force is that feeling. Now, if suddenly you were in a convertible not wearing a seatbelt and you could, levitate out of the door or whatever, then you would keep going in a straight circle, right? It's easier to think of like a little thing, a ball on a string. If I spin it around and around and around, and then I let go at one point, it's going to keep going in that straight line, right? It's not going to follow the circle anymore. It keeps going on its tangential velocity. So I would keep going on this green straight line. However, I'm going to run into the car door, and that's going to help push me inside the car to where the road goes. Great. We call that centrifugal force, but it's just a feeling. It's not actually a force. So we also call it a false force. Fictitious is another way of phrasing it. All right. Let's pause there, and we'll come back with another one for apparent weight.